Your team can rewrite that C# service in Rust. AI can produce that migration plan, draft the new service, and build a convincing benchmark all before lunch. But none of that answers this senior developer question. What measured constraint makes the rewrite actually necessary? Because an interesting solution is not the same as a necessary solution. And now that AI can make the interesting solution 10 times faster, that distinction matters more now than ever. In this video, I'm going to give you a 5-step test that you can use before a rewrite. A second runtime or another architecture pattern becomes your team's next maintenance problem. I call it localized complexity. Put the hard solution only where the hard constraint lives. You see, the debate starts with the wrong sentence. Senior .NET developers have heard some version of this in a meeting. We should rewrite this service in Rust. Or, we need to break this into microservices. Or, we should replace this framework. How about, we need another abstraction around this? Any one of those conclusions might be right. But the problem is that they are conclusions presented before anyone has actually named the constraint. So, instead of discussing evidence, the team starts comparing preferences. Someone likes Rust. Someone else trusts C#. One developer had a bad experience with a monolith, and another spent 3 years supporting a distributed system that never needed to be distributed. Now, everybody has a story, but nobody has a measurement. So here's your first rule. If you cannot state the problem without naming the tool, you're not ready to choose the tool. We need Rust is not a problem statement. But this operation uses 1.8 gigabytes of memory and it must stay below 500 megabytes. Well, that's a problem statement. We need microservices is not a problem statement. But this workflow must deploy independently because it changes 4 times more often than the rest of the system is a problem statement. Once you can name the constraint without naming the tool, you can start making an engineering decision instead of expressing a technical preference. Localized complexity means using specialized complexity only where a real measured constraint requires it. A game engine may need assembler in that one critical path. That does not mean the whole engine should be written in assembly. A C# application may have one workload that needs tighter control over memory or latency. Rust might be the right answer at that boundary. That does not mean that the entire .NET system needs a second runtime. A browser interaction may require TypeScript, but that choice does not dictate your backend stack. The point is not that Rust, TypeScript, microservices, or rewrites are bad. The point is that every technical choice creates a lifetime cost. Your team has to learn it, test it, deploy it, observe it, secure it, hire for it, and support it when the person who introduced it is no longer there. That cost may be worth paying, but it should be paid for a constraint that you can prove inside the smallest boundary that contains it. Here's the hardest 1% trap. Every mature system has an awkward part. One report processes way too much data. One integration has unusual timing rules. One workflow needs stronger isolation. One calculation sits on a very hot path, and it's a very long calculation. That trap is letting that hardest 1% dictate the architecture of the other 99%. Maybe one operation would benefit from specialized runtime. If you rewrite the whole service around that operation, then the other 99% now carries this second language, another deployment path, another security model, split observability, harder hiring, and a larger on-call burden. The code that never had the original problem becomes harder to change because it now lives inside the solution to someone else's constraint. Do not make the whole system pay rent for a constraint that lives in one room. Draw a boundary around that room. Apply the specialized solution there, and then expand that boundary only when more evidence requires it. That is not weak architecture, that is disciplined architecture. And good boundaries let you apply more power in one place without forcing the entire system to pay for it. Here's why rewrites look so clean. Rewrites make this judgment especially difficult because the comparison is unfair. The current system has visible scars. You can see awkward code. You know which deployment makes everybody nervous. You remember the customer issue that required a strange conditional 6 years ago. The replacement has none of those scars, not because it's necessarily designed better, but because it has not met production yet. The old code contains discovered requirements, customer edge cases, operational lessons, and quiet fixes nobody remembers making. The prototype looks simpler partly because it knows less. AI makes that constraint even more convincing. It can generate a clean replacement quickly. It can translate familiar code into an unfamiliar language. It can create tests around the behavior you remembered to describe. But it does not automatically know the production history that nobody wrote down. It does not know why that odd retry exists unless your engineering system gave it that context. It does not know which customer depends on behavior the team thinks is a bug. It does not know which support call led to the validation rule that now everybody just takes for granted. AI can make the rewrite 10 times faster. It cannot tell you the ongoing maintenance costs, the opportunities you'll give up, or the new corners that you're painting yourself into. That judgment still belongs to the team carrying the consequences. So here's the 5-question rewrite test. Before I approve a full rewrite, I want clear answers to 5 questions. First question, what measured constraint makes the current system unacceptable? Not old, not ugly, not annoying, unacceptable. And unacceptable according to what measurement? Is it latency, memory, throughput, failure rate, security exposure, support status, or the inability to deliver a required business outcome? Second question, can we remove that constraint inside a smaller boundary? Can we isolate one calculation, one workflow, one integration, or one domain instead of replacing the entire system? A smaller boundary gives you a smaller migration, a smaller rollback, and a smaller blast radius if your assumptions are wrong. Third question, which proven behaviors must the new system rediscover? What does production know that the prototype does not know? Look at support tickets, logs, tests, customer-specific rules, deployment history, and the parts of the code nobody wants to touch. Those are often where the real requirements are hiding. Fourth question. What operational, security, hiring, and support cost will this add? Count more than just implementation time. Who deploys it? Who monitors it? Who patches it? Who responds when it fails? Can the current team review it well? Can you hire people who can support both ecosystems? Fifth question. What customer or business result justifies the full lifetime cost? A rewrite is not successful because the new code is cleaner. It's successful because it removes a meaningful constraint from the business without creating a worse one somewhere else in the business. Now, this test does not ban rewrites. Sometimes the runtime is unsupported. Sometimes the platform is no longer safe to change. Sometimes the architecture blocks a critical business direction. Sometimes a measured bottleneck resists every smaller fix. When the evidence supports a rewrite, rewrite with clear eyes. The point is not to avoid hard choices. The point is to make the evidence carry the decision. Here's the 10-minute test. You can use a shorter version of this in your next design meeting. It takes 10 minutes, 5 steps. Step 1, state the constraint without naming a language, framework, database, or architecture pattern. If the sentence contains the tool that you already want, rewrite the sentence. Step 2, document the gap. Write down the current result and the required result. Current memory is 1.8 gigabytes. Required memory is below 500 megabytes. Current P95 latency is 1.4 seconds. The required P95 latency is below 300 milliseconds. Current deployment requires coordinating 3 teams. Required deployment must be owned by a single team. Make the gap visible. Step 3, draw the boundary. Draw the smallest component, workflow, or domain that contains that gap. Do not begin with the current service boundary. The constraint may be smaller than the service. Step 4, count development, deployment, observability, security, hiring, and support. The cheap prototype is not the full price. Step 5, choose the smallest necessary tool. Choose the simplest option that closes the measured gap. Then expand only when another proven constraint requires it. That is localized complexity. It moves the architecture conversation away from favorite tools and towards evidence, boundaries, and cost. Those are the disagreements worth having. After 29 years in software professionally, I've learned that senior development skill often looks like restraint. You don't need the least complex system possible. Real constraints sometimes demand hard solutions. You need complexity in the right place for a reason that you can measure, inside a boundary that your team can carry. So before your team rewrites that .NET service, prove the constraint. Do not optimize the whole system for its hardest 1%. Localize the complexity. I'm Chad Carter, helping developers ship production-ready software faster. You already know what you're doing, so now go and ship it. And hey, if this helped, you know the drill. Plus, if you liked it, you can share it with a developer that you like. And I'll see you in the next video.